So far we've been talking about fluid flow against an object. Now we want to talk about, we have a flat plate and we have fluid flow going over that flat plate. What's going on with the drag on the plate? And so for flow over a flat plate, we can say that the coefficient of drag is completely due to skin friction. There's no form drag here. And so we can define this friction force on a flat plate be same equation we've had before. Force of drag is equal to 1/2 C A rho V squared. The only difference here is this C, we've changed from a C sub D to a C sub F, which is the friction drag coefficient. And then also this A, now we're going to say A is that surface area of the plate that's exposed, the sort of wetted area that the fluid is flowing over. Now, in this case, the friction coefficient C sub F is going to actually vary along the plate based on the actual boundary layer. So I think on Monday you talked about the boundary layer and how it kind of grows as you go along. And so also the C sub F is going to vary. There is this, you can see the laminar flow developing here at the beginning of the plate, transition, and then finally turbulence, and then how the C sub F is going to vary along that path. If we want to know where this is going to occur, where's this transition to turbulence going to occur, we have this engineering critical Reynolds number, which is 5 times 10 to the 5th. A little bit different than the transition to turbulence Reynolds number we talked about for pipe flow. And that's going to be equal to, for a flat plate, rho times V times the characteristic length, which for a flat plate is going to be that distance to where the transition to turbulence occurs, divided by mu. So this X critical is this distance from here to here, the critical distance before we trip to turbulent flow. And that's going to be 5 times 10 to the 5th is where that's going to occur. Now how do we find C sub F itself given this? What's the equation for this curve up here? There's relationships in section 11-5 in your book. They go through and talk a lot about it, several different ones, but here's 11-5. Equation 1122 is probably the most common overall equation. There it is, right there. Oops, it's backwards. But anyway, you can look up equation 11-22 in your book. That's the most common. And so based on that, you could get C sub F, and then you could calculate what's the drag force at different, what's the drag force on the plate, and what's the drag force at different points on the plate. Because again, CF is varying over the course of the whole plate. In these relationships, you can sort of get the average friction coefficient over the entire plate, and that's what those are trying to do. Okay. So last thing is keep straight your areas for the sign that's in the example problem you'll see, or for most objects, it's going to be the frontal area for sort of blunt, broad objects. It's going to be the planform area for airfoils, wings, or highly streamlined objects. And it's going to be the wetted or surface area of a flat plate. Question: does a decrease in the drag coefficient due to increased Reynolds number indicate a decrease in drag? We talked about in the last video how the Reynolds number, or the drag coefficient, generally decreases with increasing Reynolds number. So is that going to result in a decrease in drag? Think about that for a second. So the answer is it could, but when we increase the Reynolds number, we're increasing the velocity, and the drag coefficient equations that we've talked about are proportional to velocity squared. So as we increase that Reynolds number, velocity is going up, which is increasing the overall drag due to that, even though the drag coefficient is going to be decreasing due to increased Reynolds number. So the answer is possibly, but not necessarily, and often no. Okay. So that is going to wrap up the drag lecture. Make sure you've watched all of the videos posted on the list, and then you can take the little quiz. Don't forget to watch the example problem on that calculates the drag force on speed limit sign and the bending moment that occurs at the base due to that.